Okay, so L'Hopital's rule, remember, if, basically like this, if f and g are differentiable, and I'm just going to say they're differentiable, and the limit of f of x as x approaches c is 0, and the limit of g of x as x approaches c is also 0. It could be, as we said before, they could be plus or minus infinity. Then the limit of f over g as x approaches c is the same thing as the limit of f prime over g prime as x approaches c. Okay, so that's L'Hopital's rule. The picture is like this. Right? You have a c here. You have two functions that are approaching. So you have f and you have g, say, and they're both approaching 0. Right? They're both approaching 0 as you approach c, right? And what you're saying is that if they're both approaching 0, then the limit of their ratio is actually the limit of the velocities, right? The limit of the ratio of the velocities, right? So you take at each point, you'd say, I'm going to take the velocities. I'm going to take the velocities and let the ratio of those velocities. Consider the ratio of those velocities as x approaches c. Okay, and that turns out to be the same thing as the ratio of the positions. Okay. That might seem sort of mysterious. I'm going to take a couple minutes and try and give you a sense of why this happens. Okay, this you don't have to know this. You don't have to know this, but I think it's sort of interesting. So there's something called the Generalized Mean Value Theorem. Okay, something called the Generalized Mean Value Theorem, and it says this, that so under certain conditions, so if blah blah blah, then so again, let me say it like this. So you have two functions, f and g, on AB, and they're both, f and g are continuous on the closure and differentiable on the inside, as usual. Okay, and you need one more thing that I'll put on later, but then there exists a c in AB where f prime of c over g prime of c equals f of b over f of a over g of b minus g of a. Okay, so this is sort of the, and the condition I should probably put on is that g prime is not 0. Okay, so this is sort of like the ultimate form of the mean value theorem. Right? We saw Rolle's theorem. Rolle's theorem gave us the mean value theorem. The mean value theorem gave us that funny theorem about if you have two cars and they start. If the distance at the beginning and the end is the same, then there's some point where they have exactly the same velocity, right? Right, and then there's this thing. Now this thing might look sort of strange, but let me write it in a slightly different form. If I write it like this, maybe the meaning becomes a little bit more apparent. So what's this thing on the top? What's this thing on the top in terms of, say, velocity? Or geometrically, however you want to say it. Okay?
Is it average velocity?
Yeah, this is the average velocity, right? So AB you have one function and you have another function. Okay. You have one function, you have another function. There is a place where the ratio of the instantaneous velocities equals the ratio of the average velocities over the whole interval. Okay. So if one car traveled 60 miles in that one, so it's supposed to, during 1 hour, one car travels 60 miles and the other car travels 30 miles. Well, at some point, there's a point in time where the first car is traveling exactly twice the speed of the second car. Okay. So there is a time where the ratio of the instantaneous velocities equals the ratio of the average velocities. Okay. Or geometrically, what this is saying is that there's a place where the ratio of the slopes of the tangent lines equals the ratio of the slopes of the lines through the endpoints. Okay, that's what that says. Okay. Okay. So I was gonna explain this, but you all seem kind of dead right now. But okay, so I'm not gonna tell you why this is true. I'm not gonna tell you why this is true. Although it's sort of a cool thing to see. It's sort of a cool thing to see. Well,
you're not gonna show us.
What?
You're not gonna show us.
I'm not gonna show you.
But it's cool.
It's very cool.
Can you show us?
No, I'm not gonna. Oh, okay, hold on. So, okay. Okay, so, okay, I'll do it this way. So, I'll do what I was gonna do no matter how dead you were. I'll show you how the mean value theorem gives you L'Hopital's rule. Okay, and then I guess I will show you how you get the generalized mean value theorem. Just for entertainment. We actually have a fair amount of time today. There's not too much that I want to cover today. Okay. So how does this give one? How does this give L'Hopital's rule? How does this give L'Hopital's rule? So let's go back to the picture. So you have one point A, you have another point B, right? And you have these two functions, f and g. Okay. Now let's use the generalized mean value theorem on this thing. Okay. The generalized mean value theorem says, well, there's some point, right? There's some c in AB where f prime c over g prime c. F prime c over g prime c is what? Will be f of b minus f of a. What's f of a? 0. And f of b minus 0 over g of b minus 0. Okay, so now it's starting to look good, right? It's starting to look good, right? L'Hopital's theorem is starting to take form here. So now, so one can do this for any b, right? You can do this for any b. So when I move my b, I'm going to get a new c, right? Every time I move my b a little bit closer, I'm going to get a c between a and b for which this is true, right? Is that clear? Right. So getting a c each time getting a c between a and b. So what you do is then just take the limit. Take the limit as b goes to a from the right hand side. So let b squash into a. Okay. The limit of f of b over g of b as b goes to a is the limit of f prime of c over g prime of c as b goes to a. Right? Where the c is changing each time. Right? As the b changes, the c changes. Right? So this really actually depends on b. Okay? But you see what happens as b goes to a, what happens to the c? As b moves in, what happens to the c?
Also moves in.
The c also moves in, right? So I might as well say this is the same thing actually as the limit of c going to a of f prime c over g prime c. Okay, because as b goes to a, the c goes to a. Okay, so what do you get? The limit of the ratios, right? The limit of the ratios of the function is the same thing as the limit of the ratios of the instantaneous velocities. So L'Hopital's rule. Okay, so L'Hopital's rule is just comes right out of this generalized mean value theorem. Yeah, Claire.
Why is it from C? Why did you have this from the limit from C goes to as C goes to A? Because isn't the limit as B goes to A on the left, and we just need the same like B goes to A on the bottom?
Well,
L'Hopital's rule.
if you, as long as you understand it, you could leave it this way. You could leave it this way, but just to make it more explicitly, L'Hopital's rule is like this, right? X goes to A equals the limit of f of x over g of x as x goes to A. Right, just to make it exactly in the same form, because you want you'd like the limit of f of x over g of x as x goes to A. Right, the limit of f prime c over g prime c as c goes to A.
Oh,
right, I wanted to make it exactly the same variable.
Okay.
It's true. If you understand it that as b goes to a, then c will also go to a.
Okay, I see.
But
I see.
just to make it very clear that we're taking the limit of the ratio as the point of evaluation travels close to a.
Okay, thank you.
Okay. So this is how L'Hopital's theorem works. It's actually a consequence of a mean value theorem. Okay, so just for fun, I don't know if this is fun. Okay, so here we go. I think this is sort of cool, so I'm going to show it to you. So here we go. So why is the generalized mean value theorem true? So let's recall what we had before. We had something like this. If you have two functions, and I don't think we actually had this. I'm lying to you, but we had something pretty close to this. We had if you have two functions like this, and the difference is the same. So this height. I'm just going to put a bar here. If these two differences are the same, then there's a place where f prime c equals g prime c. Did we have that? We didn't have that actually. We had something pretty similar to it.
Yeah,
Right.
didn't we have where like the points are the same?
We had the points were the same, but if the difference is this, you remember what we needed, why we had the points the same? It was so we could apply Rolle's theorem to the difference, right? But if we apply Rolle's theorem to the difference here, can we apply Rolle's theorem to the difference here? If we take the difference function, well, the height at the beginning and the end is the same, so you can use Rolle's theorem again, right? So this is just Rolle's theorem again. Okay. So now let's get this thing. So here we have something completely strange. You have two functions, and there's nothing. You're not saying anything about the values at the beginning and the end. Okay. Okay. So what you do is you. What do you think we should do? No, this is a bad question. It's too open. Here's what we're going to do. We're going to twist one of the functions so that we get a new function whose difference is the same. Okay, and then we'll use this thing on that. Okay, so here's the idea. We're going to twist the functions. Okay. So we have f and g, and now what we're going to do is multiply g by a constant, alpha. Okay, so that a alpha g of b minus f of b equals alpha g of a minus f of a. Okay, so we have two guys, f and g, right? The previous that theorem doesn't work on them. Okay? That theorem doesn't work on them, and so what we're going to do is we're going to multiply g by some number and make something that the previous theorem works on. Okay. Okay. So what's the constant? What's alpha? What alpha should we use? Can anyone see it? What should alpha be?
B minus A or anything, is it?
No. What should alpha be? You can actually figure it out from here. What should alpha be? If alpha g of b minus f of b equals alpha g of a over f minus f of a, what should alpha be? Come on. No? No? Ria?
Is it the constant difference between two endpoints?
Is it the what?
Is it the constant difference between the two endpoints?
The constant difference between the endpoints. It will result in a constant difference between the endpoints. But what number do we need to multiply? Vickers?
F prime c minus g prime c.
No, there's no c yet. There's no c yet. The answer is just solve for alpha. Right? Just solve for alpha
I
here.
just got one. Did I do that wrong?
You got it. So let's just solve for alpha. So here you get alpha g of b minus alpha g of a. We're going to move the terms involving alpha to one side, and then move the other terms to the other side. So then alpha, what should alpha be? Alpha should be this. Okay. So we multiply g by alpha, and that will result in some new function where the difference between the new function and g has the same differences at the endpoints. Okay, that's what we're doing. We're making a new function so that these two guys, the theorem can apply to them. Okay. Yeah, Claire.
Wait, so there's a constant difference between alpha g
And f.
and f.
Yeah. So g and f were no good, right? G and f were just some random guys on the street, right? There's no relation between them. Okay. But we mess with alpha, we mess with g, and we change it into something for which there is a good relation between f and this new guy. Okay. Okay. So by the result on the left, what do we know? There's a place where what happens? There's a place where what happens? There's a place where f prime c equals, not g prime c, but alpha g prime c. Right? In other words, there's a place where f prime c over g prime c equals alpha. And that's the end. Right? Okay, so you have these two functions that have no particular relation to each other, but you force the second guy to have a relation with the first one. Okay. And then you say, okay, what information do you get out of it? You get this information, that there's a place where, what does that tell you about the original two functions? That there's a place where the ratio of the instantaneous velocities equals the ratio of the average velocities. Okay, I'm sorry. Okay, let's go back to the mainstream of the lecture. Okay, but anyway, this is what we're doing L'Hopital's, so I don't feel too bad about this. I once looked on a mathematical joke website. There's like, as a math teacher, you always try to like throw in a few jokes here and there. So I thought, okay, I might as well look on the internet for mathematical jokes. And there's like all these websites of mathematical jokes. So one of them says, it's not that funny. One of them says that as a math professor, being a math professor, you have to tell the truth and nothing but the truth, but you cannot tell the whole truth. Right? Because if you start telling the whole truth, then you runs into trouble. So you see what I mean? As a teacher, sometimes you don't want to tell the whole story because, particularly this sort of thing. Anyway, I hope some of you enjoyed it. Okay, so now let's get back to what we call extending the reach of what we call. With using the logarithm function. Okay. So this is called indeterminate forms. Indeterminate forms, 0 to the 0, 1 to the infinity, and infinity to the 0. Okay. So here's how you want to think of it. Again, it's sort of a tug of war, right? If I have any number, suppose I have some positive number b, and I raise it to the 0. What do I get? 1, right? And think about 0 to the 0. And what does 0 to the 0 mean? Well, anything to the 0 is 1, right? What about 0 to the anything? 0 to any power is 0, right? So what is this 0 to the 0? It's not clear. Who wins, right? Does the base win or does the exponent win? Right? Okay. Same sort of thing. If I have something slightly bigger than 1, suppose I have something that's not 1, something bigger than 1, like 1.1, and I raise it to the infinity. What do I end up with? Infinity, right? Infinity. Now suppose I have 1 and I raise it to any power. What's 1 to any power? 1, right? So again, you're sort of wondering who wins. Does the exponent win or does the base win, right? Similarly for infinity to the 0, right? So anything to the 0 ought to be 1, but infinity to any power really ought to be infinity, right? So it's not really clear who wins, and again, it's a matter of who is faster. Okay, so it's again a thing of L'Hopital as well. Okay, so example. did I talk about the limit of x to the x as x goes to 0 from the positive side? Okay. Well, that's going to be 0 to 0, 0 to the 0. It's not really clear what it means. So what we do is we play a trick. Consider the logarithm of this limit. Okay. Consider the logarithm of this limit. Applying the log to this thing with the exponent will allow us to actually pull L'Hopital's rule into this. Okay. So, yeah, right.
Wait, I feel like I should know this, but why do you use log base e? Why do you use natural log?
Oh, it's
Thinking.
here's one way of thinking about it. Log base e is good because when you take the derivative of e to the x, you get e to the x, right? But if you do it for any other thing, then the derivative you get a to the x natural log a. Okay. So there's something more natural about using e when you talk about when you're doing calculus. Yeah. So when we always use it. Yeah. I mean, you could in this application you could use log. You could use some other log if you felt like it, but people usually use natural. Okay. So so we have this thing, natural log of the limit of x to the x as x goes to 0 on the positive side. Okay. We're going to pull the trick of continuity. Natural log is continuous, so we can pass it through the limit. Remember? Do you remember this? We did this sort of thing before. This is the same thing as the limit of the natural log of x to the x as x goes to 0. Because the natural log is continuous. Okay. Now this is good. What do I have? I've got natural log of x to the x. What can I do with that? Thea?
You become natural log of x over 1 over x.
Over 1 over x. Okay. So I'm going to write it like this: x natural log of x, or I can write it like this: natural log of x over 1 over x. And you let me leave it like this for a second. Remember, the natural log of something to a power, we pull the power in front, right? Makes the power into a factor, a multiplicative factor. Okay. Okay. And what I'm going to say is that this is something that I can apply L'Hopital's rule to. Maybe it's not evident, but as Theo just said, if I write it like this, maybe it's more evident, right? X is the same thing as 1 over x, right? So I'm just going to write it like this. And as x goes to 0 from the positive side, natural log of x goes to negative infinity, and this goes to positive infinity, right? So now it really is in the infinity over infinity form, and now we can use L'Hopital's rule on it. Okay. So what happens when you use L'Hopital's rule? Maybe take half a minute and work out what happens. Okay, who wants to tell me what happens? What's the derivative of the top? What's the derivative of natural log? 1 over x. What's the derivative of the bottom?
Negative 1 over root x.
No.
Negative x to the negative 2.
Negative x to the negative 2. Mm-hmm. Right, because you have x to the negative 1 on the bottom. The derivative of that would be negative x to the negative 2. Right. Okay, so we have x to the negative 1 on the top, x to the negative 2 on the bottom, right? So that's the same thing as negative x as x goes to 0 from the plus side, right? And so it's going to be 0.
How did you get that?
How do I get which one?
That last step.
As the limit This last part here?
No, the adding term.
From here to here?
Exactly.
Yeah. Well, this is x to the negative 1. This is x to the negative 2. Right? So when I pull it up here, it becomes x to the positive 2. Right? So I've got x to the negative 1 over x to the negative 2. You know, if you want to think of it this way, you could say I'm going to multiply on top and bottom by x squared.
Okay.
Right? And then I end up with x to the 1 on the top and x to the 0, let's just say 1 on the bottom.
Okay, that makes sense.
Okay. And so I get 0. Okay. So that tells me that the natural log of the thing I was looking for was 0. The natural log of the thing I was looking for was 0. So what's the thing I was looking for?
E to the 0.
Who said it?
E to the 0.
E to the 0. Right? So this is going to be e to the 0. Let's just say 1. So the limit of x to the x as x goes to 0 is 1. The exponent wins. Right? The base loses. So, right, the limit of x to the x as x goes to 0 is e to the 0. Let's just say 1. Okay. So yeah, Victor.
Will this be the case in any situation where you have 0 to 0?
No. No, you have to work it out. You have to work it out. It's not, so it's not always the case. You might think, oh, 0 to 0 is 0 to the 0 is always 1. But that's not true. What if I had a squared here? Right? Then you have to work out. You have to see how it goes. Right? It depends on the rates, basically.
Right.
Yeah. You have to. Every rate is. If you have different predicates, the outcome will be different. Okay. Let me do a couple more examples. Here is a 1 to the infinity type example. The limit as x goes to infinity of 1 plus 1 over x dx. Okay. You notice that this thing on the inside here becomes 1. As x goes to infinity, this thing becomes 1. The exponent goes to infinity. Again, you know, if you have something bigger than 1 and you raise it to an infinite power, you think you get infinity. But if you have 1 raised to any power, you think you should get 1, right? So is it 1 or is it infinity? It actually turns out to be somewhere in between. It balances out. The tug of war sort of balances out at a particular number. Okay, so let's do it again. So consider again the natural log of this thing. Right. Again, we pull the natural log through to get the natural log of 1 plus 1 over x. X here, as x goes to infinity. Right. Should I let you try it? I'll let you try it.
Don't let us try it.
What?
I said, don't let us try it.
I'm going to let you try it. Okay, take 1 minute and see if you can get the answer. Okay, turn to somebody next to you and say what you did, what you're doing.
need the x on the bottom.
Okay, okay. Who would like to make some suggestions?
Yeah.
Kimai, you're looking at me. Do you want to?
No, I think I got it wrong.
You think you got the wrong answer? Do you want to try and I'll sort of.
Yeah, sure. I divide, so I rewrote it as ln of 1 plus 1 over x over 1 over x.
Okay, great. So you're pulling the same trick as before,
Yeah.
right? And then you say, okay, well, this turns into 0 over 0, right? As x goes to infinity, you get natural log of 1. Natural log of 1 is 0. This thing, 1 over x as x goes to infinity is 0 also. So it's 0 over 0. We can apply L'Hopital's rule to it. And so you do, right? And what do you get?
I got 1 over 1 plus 1 over x.
1 over 1.
And
What?
then minus x negative second power all over negative x negative second power.
Oh, remember you have to take the derivative separately. You're not taking the derivative of the whole thing, right? You have to take the derivative of the top over the derivative of the bottom. So, okay, let's see. So, yeah. So the limit of the natural log of 1 plus 1 over x over 1 over x. X goes to infinity, right? Maybe you did. Okay. So what's the derivative of the top? You're going to get.
1 over 1 plus 1 over x.
So you get the derivative of this thing over this thing, right? Right, so you take the derivative of this thing, that's going to be negative 1 over x squared over this thing. Right?
Wait, don't you, isn't it like chain rule?
By the chain rule.
He just moved up the.
Wait, what did you square?
By the chain rule.
Okay.
Right? The natural log of f of x, if I differentiate this with respect to x, right? I'm going to get the derivative of the natural log evaluated at f of x, right? The derivative of the natural log evaluated at f of x, right? So I get 1 over f of x.
Okay, actually, yeah, that's what I got.
Times the derivative of the inside guy, f prime x,
Yeah.
right? So I get the derivative of, I get f prime, right? The derivative of this guy over f itself.
Yeah. Yeah.
Okay.
Yes.
Okay. Okay. And then divide that by the derivative of the bottom. The derivative of the top. The derivative of the top over the derivative of the bottom. Right? Okay. So what does that simplify to? 1 over 1 plus 1 over x, right? Right? Because we have this negative 1 over x squared, and we're dividing by negative 1 over x squared. Right? So those two cancel, and we end up with this. Okay. And so what do you end up with? 1.
Nice.
So what's the answer to the? So that's the natural log of the limit. So what does that tell us about our original limit? It's e. It balances, the tug of war balances out at a particular number, e. All
I feel
right.
like you're kind of like using E to find E though. Like if E existed, like I feel like you couldn't have solved the problem this way, right? Because natural log is like the inverse function of E. So we kind of use D to get E.
Yeah. That's a good point. That's a good point. Really, the way that one wants to introduce the natural log is to use the integral.
Oh.
Yeah. So you're right, Mariah. That there's if you look at the whole scheme, then the way we introduced, if you think that the natural log is the inverse of the exponential function, and we had e to begin with, right? Then it's circular. Yeah. So yeah, very good. That's the way actually to do things is to introduce the natural log function as an integral, and then e is going to be e to the x is the inverse function of that function. Okay. So yeah, to make it logically consistent. Yeah, good. Good. I should give you a point there on the final. At least maybe 2. Okay. Okay. So one more trick. Actually, there are 2 more tricks, and one is pretty similar to the first. So I'll do them both. I'm not going to have you work them out. So here's one: the limit of x to the 1 over x as x goes to infinity. Okay. Play the same game. You're going to take the natural log. Consider the natural log of the limit of 1 over x. X to the 1 over x, right? Well, that's the same thing as the limit of 1 over x natural log x as x goes to infinity. Right? And we actually saw this already. We have natural log over x. Remember, natural log is slow, loses to x. This ends up being 0. Right? By L'Hopital's rule. Right? And so what's this? This is going to be e to the 0, namely 1. Everyone all right with that? It's no different from the previous ones, basically. The only thing that's different is that it's a different indeterminate form. Right? It's infinity to the 0. But one approaches it in exactly the same way. Okay. Here is the last form, which I didn't even write up, maybe because it's not that fancy. Okay. Infinity minus infinity form. It sounds fancy, but really it's nothing. So here's an example. As x goes to 0, 1 over sine x minus 1 over x. Okay. So this becomes infinite. This also becomes infinite. Okay, so you've got infinity minus infinity. What do you do with it? The trick in this case is just to do elementary school algebra. Okay, so that's why I didn't even mention it. Sometimes if you just find a common denominator, you can put it into L'Hopital's rule form. Okay, so find a common denominator. Right, so this is going to be x minus sine x over x sine x. Okay, and now you see the top goes to 0 and the bottom goes to 0, right? The top goes to 0 and the bottom goes to 0, and so you can apply L'Hopital's rule to it. So it equals, by L'Hopital's rule, let's look at the derivative of the top. We get 1 minus the cosine over the derivative of the bottom, first times the derivative of the second, plus the derivative of the first times the second. Okay. But you see what that is, what happened there. You're going to end up with, again, 0 over 0. Right. So again, we need to apply L'Hopital's rule to it. Right. You end up with negative the positive sign over the derivative of the bottom, first times the derivative of the second, plus the derivative of the first times the second, plus okay. And you see what happens? You get 0 over 2. So in this case, infinity minus infinity turns out to be 0. But only because these two are basically the same infinity. If this were a faster infinity, then you wouldn't necessarily get that. Okay? And again, you can judge who's the winner by using how you can judge how the tug of war balances out by using L'Hopital's rule. Okay, that's it for today.